cosm. Whoosh.
Picture this. You're standing at what you think is the edge of the world. Beyond you, nothing but void. But then someone taps you on the shoulder and says, "Keep walking." That's where we are right now in cosmology. For nearly a century, we've been telling ourselves a story. A good story. A story that begins with a bang. The Big Bang. The moment when space, time, matter, and energy exploded into existence from an infinitely dense point. We've measured it. We've mapped it. We've even heard its echo in the cosmic microwave background radiation that bathes the universe in a faint afterglow. But here's the thing about science. Just when you think you've reached the end of the story, you realize you're only at the middle. Let me take you back to 1927. A Belgian priest and physicist named Georges Lemaitre proposed something radical. He suggested that the universe began as what he called a primeval atom. Everything that exists compressed into a single point. Then Edwin Hubble came along and confirmed that galaxies were racing away from us in all directions. The universe was expanding. Run that film backward and you get to a beginning, a cosmic genesis. We called it the Big Bang, though Fred Hoyle coined that term mockingly, preferring his own steady-state universe. But the evidence kept piling up. In 1964, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation. It was like finding the birth certificate of the universe. The case seemed closed, except it wasn't, because the Big Bang theory, as elegant as it is, has always had a dirty little secret. It doesn't actually explain the bang. It tells us what happened after, sure. 1/billionth of a second after. 1/millionth. 1 second. 3 minutes when the first atomic nuclei formed. 380,000 years when light could finally travel freely through space. But what about time zero? What about that infinitely dense, infinitely hot singularity where all the laws of physics break down? The Big Bang theory takes us to the door of creation, but it can't open it. The math literally explodes. Infinities everywhere. And in physics, when you get infinities, it usually means your theory is incomplete. So let's talk about what might have come before. The first thing you need to wrap your head around is this idea. Time itself might not have started at the Big Bang. I know. How can anything happen before time begins? Sounds like asking what's north of the North Pole. But stay with me. What if time didn't begin? What if it just changed form? What if the Big Bang wasn't a beginning, but a transition, a bounce, a rebirth? This is where cosmology gets really interesting, because we're now exploring ideas that would have seemed like pure fantasy just decades ago, but which are grounded in serious mathematics and theoretical physics. Let me introduce you to cosmic inflation. In the early 1980s, a physicist named Alan Guth proposed that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. We're talking about the universe doubling in size not once, not twice, but about 100 times in less time than it takes light to cross a proton. This inflation solved some major problems. It explained why the universe looks so uniform in all directions. It explained why space appears to be flat. It explained the origin of the cosmic structures we see today. Quantum fluctuations during inflation got stretched to cosmic scales, seeding the galaxies and clusters that would form billions of years later. Inflation was a game changer. But here's where it gets wild. If inflation happened once, why couldn't it happen again? Or better yet, why couldn't it have been happening forever? Enter eternal inflation. This is the idea that once inflation starts in some region of space, it never completely stops everywhere. Sure, it stopped in our observable universe 13.8 billion years ago, giving rise to the hot Big Bang we know and love. But beyond our cosmic horizon, inflation might still be going on. And in that eternally inflating space, quantum fluctuations are constantly creating bubble universes, pocket universes, each one with its own Big Bang, each one potentially with different laws of physics, different constants of nature, different destinies. Our universe isn't the universe. It's a universe, one bubble in an infinite cosmic foam. Now think about what this means for the concept of a beginning. If eternal inflation is real, then the Big Bang wasn't the beginning of everything. It was just the beginning of our local patch, the beginning of our bubble. The multiverse itself might have no beginning at all. It might be eternal, constantly spawning new universes, each one thinking it's the whole show. This shifts the question entirely. We're no longer asking when did everything begin. We're asking when did our everything begin. And that's a very different question. But wait, there's more. Let's talk about what came before inflation itself. Because even eternal inflation had to start somehow, right? This is where quantum cosmology enters the picture. In the 1980s, physicists like James Hartle and Stephen Hawking proposed that the universe could have emerged from quite literally nothing. Not the nothing of empty space, but the nothing of no space and no time. They used a mathematical trick called the Euclidean path integral. In this framework, time becomes imaginary. Not imaginary like make-believe, but imaginary in the mathematical sense, involving the square root of -1. In this imaginary time, the distinction between time and space blurs. The universe doesn't have a beginning in the usual sense because there's no time to mark a beginning. It just is. Hawking liked to say it this way: asking what came before the Big Bang is like asking what's south of the South Pole. The question contains a false assumption. But not everyone buys that argument. Some physicists think there was something before, a previous universe, perhaps. This brings us to cyclic cosmology, the idea that the universe goes through endless cycles of expansion and contraction. Big Bang, expansion, eventual contraction, big crunch, and then boom, another Big Bang. Rinse and repeat forever. Now, this idea isn't new. Ancient cultures had cyclic cosmologies. Hindu cosmology talks about cycles of creation and destruction spanning trillions of years. But can we make it work with modern physics? Can we avoid the singularity problem? One attempt is called the ekpyrotic universe. This model, developed by Paul Steinhardt, Neil Turok, and others, proposes that our universe exists on a three-dimensional membrane, a brain floating in a higher dimensional space. There's another brain nearby. Every trillion years or so, these brains collide. The collision produces the hot, dense state we call the Big Bang. The brains bounce apart, expand, cool down, and eventually approach each other again for another collision. The universe is eternal, but it goes through these periodic rebirths. Each cycle can last trillions of years, but from our perspective, stuck on our brain, each cycle begins with what looks like a Big Bang. The ekpyrotic model is elegant, but it has challenges. For one thing, we don't have direct evidence for extra dimensions or brains. They emerge naturally from string theory, but string theory itself remains unproven. We're dealing with mathematical elegance and theoretical consistency, not experimental data. Not yet, anyway. But here's what's exciting. These models make predictions. Subtle differences in the cosmic microwave background. Patterns in the distribution of galaxies. The properties of gravitational waves. As our instruments get better, we might actually be able to test these ideas. Speaking of gravitational waves, let's talk about what they can tell us about the early universe. In 2015, LIGO detected gravitational waves for the first time, confirming Einstein's century-old prediction. These ripples in spacetime are produced by violent cosmic events like colliding black holes or neutron stars. But there should also be a background of primordial gravitational waves, produced in the first moments after the Big Bang or whatever came before it. These waves would carry information about the universe's earliest moments, potentially revealing whether there was inflation, whether there was a bounce, whether there were previous cycles. It's like cosmic archaeology. We're trying to dig up the fossils of creation itself. Now let me tell you about one of the most mind-bending ideas in modern cosmology. It comes from Roger Penrose, the British physicist who shared the 2020 Nobel Prize for his work on black holes. Penrose has proposed something called conformal cyclic cosmology, or CCC. The idea is that the universe goes through infinite cycles, but in a way that's different from other cyclic models. Here's the key insight. At the end of each cycle, after all the stars have burned out, all the black holes have evaporated through Hawking radiation, and the universe has expanded to near infinite size, something strange happens. With no particles left to measure time, time itself becomes meaningless. The end of one universe, Penrose argues, can be mathematically mapped onto the beginning of the next. The infinite future of one cycle becomes the Big Bang of the next. There's no crunch, no collision, just a seamless transition. What's remarkable about Penrose's idea is that he claims to have found evidence for it. He and his collaborators have identified what they call Hawking points in the cosmic microwave background. These are circular patterns that could be the signatures of supermassive black holes from a previous cosmic cycle. They're final bursts of Hawking radiation leaving an imprint that survived the transition to our universe. Other scientists are skeptical. They argue that these patterns could be statistical flukes, random alignments that mean nothing. The debate continues, but win or lose, Penrose has done something important. He's shown that the idea of a pre-Big Bang universe can make testable predictions. It's no longer just philosophy, it's science. Let's zoom out for a moment and think about what all of this means. For most of human history, we had mythological explanations for the origin of the universe. Gods creating the world from chaos, cosmic eggs hatching, titans and giants. These stories served important cultural and psychological functions, but they weren't science. Then, in the 20th century, we developed the Big Bang theory. For the first time, we had a scientific origin story backed by observation and mathematics. It was revolutionary, felt like the final answer. But science doesn't do final answers. Science does better approximations. And right now, we're approximating our way past the Big Bang itself. Here's another angle. Let's talk about quantum mechanics and what it tells us about nothing. In quantum theory, nothing is never really nothing. Even in the vacuum of space, particles are constantly popping in and out of existence. Virtual particles, we call them. They borrow energy from the quantum vacuum, exist for a fleeting instant, and then annihilate back into nothingness. This isn't speculation. We've measured it. The Casimir effect, for instance, shows that this quantum jittering produces real, measurable forces. Now scale this up. If particles can emerge from nothing, why not entire universes? This is the premise behind quantum tunneling models of universe creation. The universe, in this picture, tunneled into existence from a quantum vacuum. No creator needed, just quantum mechanics doing its thing. Alexander Vilenkin, a physicist at Tufts University, has championed this idea. He describes the universe as tunneling from nothing to something, from a quantum state with no space and no time to a tiny region of inflating spacetime that then grew into everything we see. The mathematics works, at least on paper, and it leads to a startling conclusion. If one universe can tunnel into existence, so can others. Infinitely many others. We're back to the multiverse again, but this time generated by quantum processes rather than eternal inflation. Or maybe it's both. Maybe quantum tunneling creates universes that then undergo inflation, which creates more universes through eternal inflation. It's universes all the way down. Now I want to address something that might be bugging you. If the Big Bang wasn't the beginning, why do we still call it the Big Bang? Good question. The answer is partly historical and partly practical. The Big Bang, as we understand it, marks a genuine transition in the history of our observable universe. It's the point before which we can't see, the cosmic event horizon beyond which our telescopes can't penetrate. It's the moment when our local region of spacetime began its current expansion phase. Whether there was something before, it doesn't change the fact that it represents a boundary in our cosmic history. It's like asking whether dawn is the beginning of the day. Sure, there was night before dawn, and the Earth was spinning through space long before the sun rose. But dawn still marks the start of the day in a meaningful sense. The Big Bang is our cosmic dawn. Let me take you on a journey through time or before time, depending on how you look at it. Imagine we're in a time machine that can travel backward, not just through history, but through cosmic history. We start now 13.8 billion years after the Big Bang. We see galaxies, stars, planets, the cosmic web of large-scale structure. We travel back. Galaxies become younger, smaller, bluer. Stars are forming at prodigious rates. We go back further. The first galaxies are just assembling. The first stars are igniting, their light beginning to ionize the hydrogen fog that fills the universe. Back further still. There are no stars yet, no galaxies, just neutral hydrogen and helium gas cooling in the expanding universe. We reach 380,000 years after the Big Bang. This is the surface of last scattering, the moment when the universe became transparent and light could travel freely. This is what we see when we look at the cosmic microwave background. We keep going back into the opaque era when the universe was too hot for atoms to hold together. Free electrons scattered photons in every direction. The universe was a glowing plasma. Back further, 3 minutes after the Big Bang, nuclear fusion in the early universe is forging the first atomic nuclei. Hydrogen, helium, a bit of lithium. The cosmic kitchen that set the stage for everything to come. Back further, 1 second after the Big Bang. It's too hot for nuclei to form. We're in a sea of protons, neutrons, electrons, neutrinos, and photons. Back to a millionth of a second. Quarks are combining to form protons and neutrons for the first time. Before this, it was too energetic even for protons to exist. Just a quark gluon plasma. And then we reach the wall. The Planck time, 10 to the minus 43 seconds after the Big Bang. This is as far back as our current physics can take us. At this scale, quantum effects of gravity become dominant, and we don't have a theory of quantum gravity. General relativity breaks down. Quantum mechanics breaks down. The singularity theorems of Penrose and Hawking tell us that at this point, classical spacetime ceases to have meaning. But is this really the end of the road? Or is it just the limit of our current understanding? This is where theories of quantum gravity come in. String theory, loop quantum gravity, causal dynamical triangulations. These approaches attempt to merge quantum mechanics and general relativity into a single framework. And they all suggest that something happens at the Planck scale that resolves the singularity. In loop quantum gravity, for instance, the gravitational attraction that would normally crush matter to infinite density is counteracted by quantum pressure. The result is a bounce. The universe contracts to a minimum size about 1 billion trillion times smaller than a proton, and then rebounds in a big bounce. What we call the Big Bang is really the outward phase of this bounce. And before the bounce, there was a previous universe, contracting down to the Planck scale before bouncing back. The big bounce is appealing because it avoids the singularity problem entirely. There's no point of infinite density, no breakdown of physics, just a smooth transition from contraction to expansion. It also suggests that the universe could be far older than 13.8 billion years. That's just the age since the most recent bounce. The universe itself could be eternal, bouncing forever between expansion and contraction. But there are challenges. For the bounce to work, you need to violate the classical energy conditions that Einstein's equations normally require. You need exotic matter or fields with negative pressure. It's possible, but it requires ingredients we haven't yet confirmed exist. Let's talk about dark energy for a moment because it's relevant here. In 1998, astronomers discovered that the expansion of the universe is accelerating. Something is pushing space-time apart, working against gravity. We call this something dark energy, and it makes up about 68% of the universe's energy content. We don't know what it is. The leading candidate is vacuum energy, a cosmological constant, the energy of empty space itself. If dark energy is real and constant, it has profound implications for the future of the universe. Galaxies will accelerate away from us. Eventually, in trillions of years, distant galaxies will recede faster than light can travel, disappearing beyond our cosmic horizon. The universe will become cold, dark, and lonely. But here's the twist. What if dark energy isn't constant? What if it changes over time? Some models of dark energy, called quintessence models, allow for this possibility. And if dark energy can change, the future becomes much less certain. The universe might not expand forever. It might slow down, stop, and recollapse. Or dark energy might ramp up, tearing apart galaxies, stars, planets, atoms, and even space-time itself in a big rip. But here's where it connects to the question of a beginning. If dark energy behaves in certain ways, it could create the conditions for a bounce or a transition to a new cycle. The ekpyrotic models I mentioned earlier use fields similar to dark energy to drive the collision of brains. Penrose's conformal cyclic cosmology requires that dark energy dominates in the far future, setting the stage for the transition to the next cycle. Understanding dark energy isn't just about predicting the future. It's also about understanding the past and whether the Big Bang was truly the beginning. Now let's get into something really speculative but fascinating: the holographic principle. This idea, which emerged from black hole thermodynamics and string theory, suggests that all the information contained in a volume of space can be encoded on the boundary of that space. It's like the universe is a hologram, a three-dimensional projection of information stored on a two-dimensional surface. If the holographic principle is correct, and many physicists think it is, it has radical implications for how we think about the Big Bang. Some researchers have proposed that what we perceive as the Big Bang could be a holographic projection of processes occurring on a lower dimensional boundary. In this view, the three-dimensional universe we inhabit, with its history of expansion from a hot, dense state, is a holographic image. The real action is happening elsewhere, in a lower dimensional space that we can't directly perceive. It's trippy, I know, but it's grounded in solid physics. Let me tell you about another mind-bending possibility: the cosmological natural selection hypothesis, proposed by Lee Smolin. The idea is that universes reproduce through black holes. When a black hole forms and collapses to a singularity, instead of everything ending, a new universe is born on the other side. This new universe inherits slightly modified physical constants from its parent universe, like genetic mutations. Over countless generations, universes evolve. Those with physical constants that favor the formation of many black holes have more offspring. Those that don't, dead end. Our universe, with its particular values for the fundamental constants, exists because it's descended from a long line of black hole prolific ancestors. This would explain why the constants of nature seem fine-tuned for complexity. Not because of design, but because of selection. Now, Smolin's idea is highly speculative and currently untestable. But it's a perfect example of how scientists are thinking outside the box when it comes to the question of cosmic origins. We're not satisfied with saying the Big Bang was the beginning and leaving it at that. We want to know why there was a Big Bang. What set it up? What came before? What lies beyond? Here's another approach: the no-boundary proposal of Hartle and Hawking that I mentioned earlier. Let me dig deeper into that. In classical cosmology, the Big Bang singularity is a boundary where space-time begins. Time has a first moment. But in quantum cosmology, Hartle and Hawking argued, there's no boundary. The universe is finite but boundless, like the surface of a sphere. Just as you can travel around the surface of the Earth without ever hitting an edge, you can trace back through the history of the universe without ever reaching a beginning. Time smoothly transitions to space in the early universe. There's no moment of creation, just a seamless quantum geometry. It's beautiful mathematics, but whether it describes reality is another question. The problem with quantum cosmology is that it's almost impossible to test. We're talking about processes at energies and scales far beyond anything we can recreate in a laboratory or observe with telescopes. But maybe not forever. Let's talk about the future of cosmology and how we might actually test some of these ideas. First, there's the cosmic microwave background. We've already mapped it in exquisite detail with satellites like COBE, WMAP, and Planck. But there's more information to extract. The CMB is polarized, and the pattern of polarization carries information about gravitational waves from the early universe. If we can detect B-mode polarization at large angular scales, it would be smoking gun evidence for cosmic inflation. It would also constrain the energy scale of inflation, telling us how close to the Planck scale inflation occurred. This would help us understand whether quantum gravity effects were important during inflation, which in turn could tell us about pre-inflationary physics. Then there's gravitational wave astronomy. We've only just begun. LIGO and Virgo detect high-frequency gravitational waves from stellar mass objects. But to probe the early universe, we need to detect much lower frequency waves. That's what space-based detectors like LISA, the Laser Interferometer Space Antenna, will do. Launched in the 2030s, LISA will detect gravitational waves from supermassive black hole mergers, but it might also detect a stochastic background of primordial gravitational waves. These could carry signatures of phase transitions in the early universe, cosmic strings, or even echoes from a previous cosmic cycle. we're on the verge of opening up an entirely new window on the early universe. There's also the possibility of direct detection of relics from before the Big Bang. Some cyclic models predict the existence of exotic particles or fields that persist from one cycle to the next. These could potentially be detected in high-energy particle collisions or in precision cosmological observations. We haven't found them yet, but absence of evidence isn't evidence of absence. The search continues. Let's talk about the anthropic principle for a moment because it's relevant to this whole discussion. The anthropic principle, in its weak form, simply states that we observe the universe to have properties compatible with our existence because if it didn't, we wouldn't be here to observe it. In its strong form, it suggests that the universe must have properties that allow observers to exist at some point. This becomes interesting when you combine it with the multiverse. If there are countless universes with different physical constants, then it's no surprise that we find ourselves in one where the constants allow for stars, planets, and life. We couldn't exist in the others. This neatly explains the apparent fine-tuning of our universe without invoking design. But it's also somewhat unsatisfying. It doesn't predict anything. It just says, well, of course things are this way. Some physicists love the anthropic principle. Others hate it. But in the context of eternal inflation or cosmological natural selection, it becomes a useful tool for thinking about why our universe is the way it is. Now, I want to take a step back and address a philosophical question. Does it even make sense to talk about what came before the Big Bang? Some argue that time itself is a feature of our universe, and asking what came before time began is nonsensical. Others argue that time might be more fundamental than we think, that it existed in some form even before our universe. This gets into deep questions about the nature of time. Is time an emergent property, something that arises from more fundamental physics? Or is it fundamental itself? Different theories of quantum gravity have different answers. In string theory, time is usually considered fundamental. In some versions of loop quantum gravity, time emerges from more basic quantum relationships. If time is emergent, then asking what came before the Big Bang might indeed be meaningless. But if time is fundamental, then there's no reason it couldn't have existed before our universe. Here's a thought experiment. Imagine you're a two-dimensional creature living on the surface of a balloon. Your universe is this two-dimensional surface. As the balloon inflates, your universe expands. Every point is moving away from every other point. Now, a smart two-dimensional physicist on the balloon might run the expansion backward and conclude that at some point in the past, the entire universe was concentrated at a single point. But from our three-dimensional perspective, we can see that the balloon had a finite size even when it was small. It wasn't actually a point. It was just a very small balloon. Maybe the Big Bang is like that. Maybe what appears to us as a singularity is actually a finite but very small structure when viewed from a higher dimensional perspective. The ekpyrotic universe and other brain cosmology models are essentially this idea made rigorous with mathematics. Let's talk about observational challenges. The problem with all these pre-Big Bang scenarios is that they're incredibly hard to test. The Big Bang itself acts like a cosmic firewall, obscuring anything that came before. Information might not propagate through the bounce or the phase transition. Even if it does, the signal might be so weak or so diluted by subsequent evolution that we can't detect it. But there's hope. Different models make different predictions about subtle features in the cosmic microwave background, the distribution of galaxies, the spectrum of gravitational waves. As our instruments improve, we're starting to distinguish between models that once seemed impossible to test. The next generation of CMB experiments, gravitational wave detectors, and large-scale structure surveys will give us unprecedented precision. We might actually be able to rule out some ideas and support others. Consider the implications if we confirm that the Big Bang wasn't the beginning. It would be one of the greatest revolutions in human thought. For thousands of years, humans have grappled with the question of cosmic origins. Every culture has its creation myths. In the 20th century, science gave us the Big Bang, a creation event grounded in observation and mathematics. But if the Big Bang was just a transition, just one event in an eternal or vastly older cosmos, it would fundamentally change how we see our place in the universe. We'd go from being inhabitants of a universe with a definite beginning to inhabitants of a potentially eternal cosmos. That's profound. It would also raise new questions. If the universe is eternal, or if it's just one bubble in an eternal multiverse, what does that mean for ideas like cosmic purpose or meaning? I'm not suggesting the universe needs to have a purpose. Science doesn't deal in purposes. It deals in mechanisms. But humans care about meaning, and our cosmology inevitably influences our philosophy. An eternal cosmos is a different stage for the human drama than a cosmos with a beginning. Let me tell you about some of the people pushing these ideas forward. Paul Steinhardt at Princeton, who developed the ekpyrotic model and has been a leading critic of cosmic inflation, arguing that it makes too many untestable predictions. Roger Penrose at Oxford with his conformal cyclic cosmology. Abe Ashtekar at Penn State, one of the founders of loop quantum gravity and a proponent of the Big Bounce. Laura Mersini-Houghton, who has proposed that quantum entanglement between universes in the multiverse could leave observable signatures in our cosmic microwave background. These scientists are explorers not of physical space, but of conceptual space. They're pushing the boundaries of what's possible, using mathematics and physics to probe questions that once seemed purely philosophical. And then there are the experimentalists and observers. The teams running the Planck satellite, the South Pole Telescope, the Atacama Cosmology Telescope, the LIGO and Virgo collaborations, the scientists planning LISA and other future missions. They're the ones who will ultimately test these theories. Science isn't just about having clever ideas. It's about testing them against reality. That's what separates science from philosophy or theology. We can imagine any number of scenarios for what came before the Big Bang, but only those that make testable predictions are scientific. Here's something that blows my mind. If eternal inflation is correct, then right now, at this very moment, new universes are being born in the inflating space beyond our cosmic horizon. Entire Big Bangs, complete with galaxies and stars and possibly life, are igniting in regions we can never see or reach. Each one thinks it's the whole universe, just like we do. It's humbling and awe-inspiring at the same time. It means the universe is far grander than we ever imagined, but also that we're far more isolated. We can never travel to these other universes. They're expanding away from us faster than light can travel. We're stuck in our bubble and they're stuck in theirs. But maybe that's okay. There's plenty to explore in our own universe. We haven't even fully explored our own solar system, much less our galaxy or the broader cosmos. We have billions of galaxies to study, each with billions of stars. We're searching for exoplanets, looking for biosignatures, trying to answer the question of whether we're alone. These are monumental endeavors, and yet we're also capable of asking questions that transcend our observable universe. We can use mathematics and physics to probe the nature of reality at the deepest levels. We can ask what came before the Big Bang and have serious scientific discussions about it. That's remarkable. Let's talk about some of the mathematical tools physicists use to explore these ideas. One key tool is the Wheeler-DeWitt equation, a quantum mechanical equation for the wave function of the universe. In standard quantum mechanics, you have a wave function that evolves in time according to the Schrödinger equation. But in quantum cosmology, you're trying to describe the entire universe, including time itself. So the wave function doesn't evolve in time. It just is. The Wheeler-DeWitt equation is timeless. It describes all possible configurations of the universe and their relative probabilities. Solving it is incredibly difficult. In fact, exact solutions exist only for the simplest toy models. But it gives us a framework for thinking about the quantum nature of the cosmos. Another tool is the path integral formulation of quantum mechanics. Developed by Richard Feynman, this approach says that to calculate the probability of a quantum system going from one state to another, you sum over all possible paths connecting those states, weighted by their action. In quantum cosmology, you apply this to entire universes. You sum over all possible geometries of spacetime, all possible histories of the universe. The Hartle-Hawking no-boundary proposal uses this approach. They sum over compact Euclidean geometries, spacetimes with no boundary. The result is a wave function that describes the probability of the universe having certain properties. Then there's the mathematics of extra dimensions. String theory requires 10 or 11 dimensions of spacetime, depending on the version. Where are these extra dimensions? Compactified, curled up into tiny shapes far smaller than anything we can observe. The geometry of these compact dimensions determines the physics we observe in our three large spatial dimensions. The ekpyrotic model and other brain cosmologies use this framework. Our universe is a three-dimensional brain embedded in a higher dimensional bulk. Other brains could exist in the bulk, possibly carrying other universes. When brains collide, the energy of the collision produces the hot dense state we call the Big Bang. It's a geometric explanation for cosmic origins. Loop quantum gravity takes a different approach. It doesn't require extra dimensions. Instead, it quantizes spacetime itself. At the Planck scale, spacetime isn't smooth and continuous. It's granular, made of discrete quantum units. These units, called spin networks, have a minimum size. Below this scale, distances and times are meaningless. This discreteness prevents singularities. When you try to compress spacetime to infinite density, the quantum discreteness kicks in and causes a bounce. The universe can't collapse to a point. It bounces back. This leads naturally to the big bounce scenario. What's exciting is that these different approaches, string theory and loop quantum gravity, despite starting from very different assumptions, sometimes arrive at similar conclusions. Both suggest that the Big Bang singularity is resolved. Both allow for pre-Big Bang scenarios. This convergence gives us some confidence that we're on the right track, even if we don't yet know which approach is correct. Now let me address a common misconception. When physicists talk about the universe coming from nothing, they don't mean nothing in the colloquial sense. They mean a quantum vacuum, a state with no particles but which still has properties. It has quantum fields that can fluctuate. It has energy even if that energy is at its minimum. This quantum nothing is still something. True nothing, absolute nothingness with no properties whatsoever, might not even be a coherent concept in physics. As the philosopher Parmenides said more than 2,000 years ago, from nothing, nothing comes. If there's absolutely nothing, not even quantum fields or the laws of physics, then there's no mechanism for anything to arise. But a quantum vacuum, that's different. It's governed by laws, can evolve. It can tunnel into a classical spacetime. This is what physicists mean when they talk about universe from nothing scenarios. But this raises a deeper question. Where do the laws of physics come from? If the universe arose from a quantum vacuum governed by quantum mechanics, what made quantum mechanics? What made the laws? This is the ultimate question, and science may never answer it. Science is good at explaining how things work, not why there's something rather than nothing. Some philosophers and scientists argue that the laws of physics are necessary truths, that they couldn't be otherwise. Others argue that the laws themselves might be contingent, that different universes in the multiverse might have different laws. Still others argue that the laws emerge from something even more fundamental, some mathematical structure or logical principle. Max Tegmark has proposed the mathematical universe hypothesis. The idea is that the universe isn't just described by mathematics. It is mathematics. Physical existence and mathematical existence are the same thing. Every self-consistent mathematical structure exists physically as some universe. Our universe is one such structure. This would explain why mathematics is so unreasonably effective at describing nature. It's not that nature follows mathematical laws. Nature is mathematical. It's a beautiful and bold idea, though also unfalsifiable and thus not really scientific in the traditional sense. Let me bring this back to something more concrete. What experiments are being done right now that could shed light on pre-Big Bang physics? The Large Hadron Collider at CERN is colliding protons at energies high enough to probe physics at smaller distances than ever before. While it's nowhere near the Planck energy where quantum gravity becomes important, it's testing our theories of particle physics and potentially revealing new physics that could inform cosmology. The discovery of the Higgs boson in 2012 was a triumph, confirming the mechanism by which particles get mass. Future colliders might discover supersymmetric particles, extra dimensions, or other exotic phenomena predicted by theories like string theory. Then there are tabletop experiments looking for violations of fundamental symmetries or anomalous forces. If extra dimensions exist, they might produce detectable effects at millimeter scales or smaller. Experiments using torsion pendulums, atom interferometers, or trapped ions are searching for these effects. So far, nothing. But the absence of evidence constrains the theories. Each null result tells us something about what's not there. And of course, there's cosmology itself. Every time we map the cosmic microwave background with greater precision, every time we survey more galaxies, every time we detect a new gravitational wave, we're gathering data that constrains models of the early universe. Sometimes the most important results are negative. We thought we'd see certain signatures, and we didn't. That rules out some models and forces us to refine others. Science progresses as much by elimination as by confirmation. Let's talk about the role of philosophy in all this. Some scientists dismiss philosophy as useless, but that's short-sighted. Philosophy helps us clarify our concepts and assumptions. What do we mean by time? By causation? By nothing? These are philosophical questions that underlie the scientific ones. Moreover, when we're dealing with untestable or barely testable ideas, the line between science and philosophy blurs. We need to think carefully about what kinds of evidence would support or refute a theory. We need to consider whether a theory that makes no testable predictions can be considered scientific. These are not easy questions, and they require philosophical analysis. Karl Popper famously argued that for a theory to be scientific, it must be falsifiable. There must be some observation that, if made, would prove the theory wrong. By this criterion, many multiverse theories are problematic. If other universes are in principle unobservable, how can we ever test the theory? Some physicists argue that we should relax the criterion. A theory can be scientific if it's part of a larger framework that does make testable predictions. For example, eternal inflation makes specific predictions about the CMB, even if the other bubbles it predicts are unobservable. Others argue that we should stick to strict falsifiability and avoid speculating about things we can't test. I don't have a definitive answer. Science is a work in progress. The rules aren't set in stone. What's important is that we keep asking questions, keep pushing the boundaries, and remain open to revising our ideas when the evidence demands it. That's the scientific spirit. Now let's consider the sociological aspect. Why are so many physicists interested in pre-Big Bang cosmology? Partly it's intellectual curiosity. These are deep questions about the nature of reality, and humans are naturally curious. But there's also a practical motivation. Understanding the early universe helps us understand fundamental physics. The energies and conditions present in the first moments after, or possibly before, the Big Bang are far beyond anything we can recreate on Earth. The early universe is a natural laboratory for testing theories of quantum gravity, particle physics beyond the standard model, and the behavior of matter and energy at extremes. By studying cosmology, we're doing fundamental physics. There's also a cultural dimension. Cosmology captures the public imagination in a way that few other sciences do. People care about where we came from. They want to know if the universe had a beginning. They want to know if there are other universes. This public interest translates into funding for research, support for space missions, and students choosing to study physics and astronomy. That's good for science as a whole. But we also need to be careful not to oversell. The media loves bold claims. Universe from nothing, time before time, infinite multiverses. These make great headlines, but they can give the impression that we know more than we do. It's important to communicate the speculative nature of some of these ideas. They're possibilities, not certainties. They're frameworks for thinking about the origin of the universe, but they're not yet confirmed by observation. As scientists, we have a responsibility to be clear about what we know, what we think we know, and what we're just guessing at. Let me give you a sense of the timescales we're dealing with. The observable universe is 13.8 billion years old. That's the time since the Big Bang. But if the cyclic models are correct, each cycle could last trillions of years. The universe we observe is just a tiny fraction of one cycle. If the big bounce happened, the previous contracting phase could have lasted hundreds of billions or trillions of years. And if eternal inflation is correct, The multiverse has been inflating forever with no beginning. Our universe, 13.8 billion years old, is an infant, a newborn in an eternal cosmic nursery. Or consider this. If Penrose's conformal cyclic cosmology is correct, the universe will undergo countless future cycles. Stars will die. Galaxies will disperse. Black holes will evaporate. After perhaps a googol years, 10 to the 100 years, the universe will transition to the next cycle. And that cycle will last just as long. And the one after that, forever. The universe had no beginning, and it will have no end. Just an eternal succession of cycles, each one lasting unimaginably longer than the current age of the universe. It makes our existence seem fleeting and insignificant, but it also means we're part of something truly eternal. How do we cope with these mind-boggling scales? It's easy to feel overwhelmed. The universe is vast and old and possibly eternal. We're tiny, short-lived, confined to a small planet orbiting an average star in an unremarkable galaxy. But here's the thing. We're the part of the universe that can think about the universe. We're conscious, intelligent beings capable of asking questions about cosmic origins. We can do math. We can build telescopes and particle accelerators. We can probe the first moments of creation and speculate about what came before. That's extraordinary. We might be insignificant in terms of size or duration, but we're significant in terms of capability. We're cosmology's way of understanding itself. Let me tell you about the concept of cosmic horizons, because it's central to understanding what we can and can't know. The observable universe has a finite size, not because the universe itself is finite, but because light has only had a finite time to reach us. We can only see out to a distance where light has had time to travel since the Big Bang. Beyond that, there's more universe, but we can't see it. The observable universe is about 93 billion light-years in diameter. But the actual universe could be much, much larger. It might even be infinite. Similarly, if there was something before the Big Bang, there's a horizon beyond which we can't see into the past. Information from before the Big Bang might not propagate through to us. Or if it does, it might be so distorted or diluted that we can't interpret it. This is frustrating. There might be an entire history, an entire cosmos, that we can never access. But it's also humbling. It reminds us that there are limits to what we can know. Science is powerful, but it's not omniscient. That said, we keep pushing those limits. Every time someone says we can never know something, someone else finds a clever way to test it. 100 years ago, people thought we could never know what stars are made of. Then we developed spectroscopy and discovered that stars are mostly hydrogen and helium. 50 years ago, people thought we could never detect gravitational waves. Then we built LIGO and detected them. Who knows what we'll achieve in the next 50 or 100 years? Maybe we'll find a way to probe pre-Big Bang physics. Maybe we'll detect signals from other universes. Or maybe we'll discover that the question itself was misconceived, that there's a deeper layer of reality we haven't yet imagined. That's the beauty of science. We don't know what we don't know, but we keep looking. Let's talk about the role of dark matter in all this. Dark matter makes up about 27% of the universe's energy content. We know it's there because of its gravitational effects on galaxies and galaxy clusters. But we don't know what it is. The leading candidates are weakly interacting massive particles, or WIMPs, but decades of searching haven't found them. Other possibilities include axions, sterile neutrinos, or even primordial black holes. Understanding dark matter is crucial for cosmology because it played a key role in the formation of structure. Dark matter clumped together first, creating gravitational wells into which ordinary matter fell, eventually forming galaxies and stars. But here's where it connects to pre-Big Bang scenarios. Some models predict that dark matter, or at least some fraction of it, could be a relic from before the Big Bang. If there was a previous universe or a previous cycle, particles or fields from that era might have survived the transition. They'd be incredibly dilute, but they could make up part of the dark matter we observe today. This is highly speculative, but it shows how pre-Big Bang physics could have observable consequences in our universe. Similarly, some models predict the existence of cosmic defects, topological features in spacetime left over from phase transitions in the early universe. These include cosmic strings, domain walls, and monopoles. While we haven't detected any of these, their presence or absence constrains early universe models. If certain pre-Big Bang scenarios are correct, they might produce or forbid certain types of defects. So by searching for these exotic structures, we're indirectly probing the question of what came before. Now I want to talk about emergence. This is the idea that complex phenomena can arise from simple underlying rules. Consciousness emerges from neurons. Life emerges from chemistry. Chemistry emerges from atoms. Atoms emerge from quarks, electrons, and photons. At each level, new properties appear that weren't obvious from the lower level. Maybe space-time itself is emergent. Maybe at the most fundamental level, there's no space and no time, just some more basic quantum information or mathematical structure. Space-time emerges from this substrate at larger scales. If this is true, then asking what came before the Big Bang is asking the wrong question. There was no before because time itself emerged at the Big Bang. What we should be asking is what is the more fundamental structure from which space-time emerged. This is an active area of research. Scientists are exploring ideas like the holographic principle, where space-time is a holographic projection of information on a lower dimensional boundary, or tensor networks, mathematical structures that encode quantum entanglement and from which space-time geometry can be reconstructed, or causal sets, discrete structures of events related by causality, from which continuous space-time emerges. These approaches are still in their infancy, but they represent a radical shift in how we think about space and time. If space-time is emergent, then the Big Bang isn't the origin of everything. It's the origin of classical space-time. But the more fundamental quantum structure from which space-time emerges might have existed before, in some sense. Or it might be timeless, not existing before or after but simply existing. This is hard to wrap your head around, but it's no harder than quantum mechanics or relativity, which also defy common sense. Let me tell you a story. In the 1960s, a young physicist named Stephen Hawking, along with his colleague Roger Penrose, proved a set of theorems about singularities in general relativity. They showed that under very general conditions, if the universe is expanding and governed by Einstein's equations, then tracing back in time inevitably leads to a singularity, a point where density and curvature become infinite and the equations break down. This was a powerful result. It seemed to prove that the Big Bang singularity was unavoidable. The universe had a beginning, but later Hawking changed his mind. He realized that when you account for quantum mechanics, the singularity theorems don't necessarily apply. Quantum effects could smooth out the singularity. This led him to develop the no-boundary proposal with James Hartle. The beginning of the universe, if you can call it that, wasn't a sharp moment in time but a smooth quantum transition. Hawking's willingness to revise his views based on new insights is a perfect example of the scientific process. We follow the evidence and the logic wherever they lead, even if it means abandoning ideas we once championed. Now let's consider the implications for the ultimate fate of the universe. If the Big Bang wasn't the beginning, maybe the Big Freeze or Big Rip won't be the end. In cyclic models, the universe undergoes periodic rebirths. Death and rebirth forever. In eternal inflation, our bubble might eventually decay or collide with another bubble, ending our universe but not the multiverse. In Penrose's CCC, the far future becomes the next Big Bang. These scenarios suggest that the universe, in some form, is eternal. There's no final end, just ongoing transformation. But even if our particular universe has a finite lifetime, the fact that it's part of a larger eternal cosmos means that existence itself continues. There's something comforting about that. We might be ephemeral, but the cosmos endures. Then again, it's also a bit terrifying. An eternal universe, constantly cycling or constantly spawning new bubbles, with no ultimate purpose or destination. Just endless existence. How do we find meaning in that? I don't have an answer. These are existential questions that each person has to grapple with in their own way. Science can't tell you how to find meaning. It can only tell you what is, not what ought to be. Let's return to the evidence. What would constitute definitive proof that the Big Bang wasn't the beginning? It's hard to say. We'd need to detect some signature that unambiguously points to pre-Big Bang physics. Maybe anomalies in the cosmic microwave background that can't be explained by inflation alone. Maybe a background of gravitational waves with a specific spectrum predicted by a bounce or collision. Maybe exotic particles that could only have been produced in a previous cycle. The challenge is that many of these signals are subtle and easily confused with foregrounds or systematics in the data. But let's say we do find something. Let's say we detect a pattern in the CMB that precisely matches the prediction of Penrose's CCC, or we detect gravitational waves with the signature of a big bounce. What then? We'd have strong evidence that the Big Bang wasn't the beginning. But we wouldn't have proof. Science doesn't do proof. It does best available explanations. There could always be alternative explanations we haven't thought of. The history of science is full of examples where data was interpreted one way and later reinterpreted completely differently. We'd need multiple independent lines of evidence, all pointing to the same conclusion, before we could be confident. And even then, we'd remain open to revision. That's the nature of science. It's provisional. It's always subject to change based on new evidence. But that's also its strength. Science doesn't claim absolute truth. It claims progress toward truth. We get better and better approximations. The Big Bang Theory is a better approximation than ancient creation myths. Pre-Big Bang cosmology, if confirmed, would be a better approximation still. And someday, we might have an even better approximation that supersedes all of these. I want to emphasize that science is a collective effort. No single person is solving these problems. It's a global community of thousands of scientists, all contributing pieces to the puzzle. Theorists develop models. Observers and experimentalists test them. Engineers build the instruments. Mathematicians provide the tools. Students learn and eventually contribute their own ideas. It's a beautiful example of human cooperation. We might be divided by politics, culture, and geography, but in science we share a common goal: understanding the universe. And the public plays a role too. You watching this are part of the scientific enterprise. Your curiosity drives funding for research. Your support enables space missions and particle accelerators. Your questions inspire scientists to communicate better. Science isn't an ivory tower activity. It's a human endeavor, and it belongs to all of us. That's why I'm making this video, to share these ideas with you, to invite you into the conversation. So where do we stand? The Big Bang Theory remains the best description we have for the early universe. But it's incomplete. It doesn't explain what happened at time zero, and it doesn't explain what, if anything, came before. We have several promising ideas, from inflation to cyclic universes to quantum cosmology to multiverse scenarios. Each has strengths and weaknesses. None has been definitively confirmed. We're in an exciting phase of exploration, where the tools are finally becoming sensitive enough to test these ideas. The next few decades will likely bring major breakthroughs. But even if we don't find the answer in my lifetime, that's okay. Science is a multi-generational project. We're building on the work of Einstein, Hubble, Hawking, and countless others. Future scientists will build on our work. Knowledge accumulates. Each generation sees a bit further. As Newton said, "If I have seen further, it is by standing on the shoulders of giants." We're all standing on those shoulders, looking out at the cosmic horizon, trying to see what lies beyond. In the end, whether the Big Bang was the beginning or not doesn't change the fact that we exist. We're here now on this planet, in this galaxy, in this universe. We have lives to live, relationships to cherish, problems to solve. The cosmos doesn't care whether we understand it. It doesn't need our comprehension to exist. But we care. We want to understand. That's what makes us human. We're the universe's way of asking questions about itself. And in that sense, cosmology isn't just science. It's philosophy. It's art. It's an expression of the human spirit. So the next time you look up at the night sky, think about this. Those stars, those galaxies, that cosmic microwave background permeating all of space, they might not be the beginning. They might be chapter 2 or chapter 2 million in a story that has no beginning and no end. A story that's still being written. And you're part of it. We all are. We're brief flickers of consciousness in an impossibly eternal cosmos. asking questions that our ancestors couldn't have dreamed of, and preparing the way for descendants who will ask questions we can't yet imagine. The Big Bang may not be the beginning after all, but wherever the universe came from, however it got here, one thing is certain. It's brought us to this moment, where we can stand in awe and wonder, and reach out with our minds to touch the very fabric of reality. And that, in itself, is a kind of miracle. Not a supernatural miracle, but a natural one. The miracle of consciousness, of curiosity, of science. The universe is vast and ancient and possibly eternal. And we get to be part of it, if only for a cosmic instant. Make the most of it. Thank you for joining me on this journey. Keep looking up. Keep asking questions. And remember, in the grand cosmic story, the most remarkable chapter might be the one where the universe woke up and started wondering about itself. That chapter is us. And our story is just beginning. Let's dig deeper into something we haven't fully explored. The information paradox at cosmic scales. You've probably heard about the black hole information paradox, where information seems to disappear when matter falls into a black hole, violating quantum mechanics. But there's a similar paradox at the cosmological level. If the Big Bang was preceded by a contracting phase, what happened to all the information from that previous universe? Did it get erased at the bounce? Did it get scrambled beyond recognition? Or is it somehow encoded in the structure of our universe? This isn't just academic hair-splitting. Information conservation is a fundamental principle in physics. Quantum mechanics demands that information cannot be destroyed, only transformed. If information from a previous cosmic cycle was lost, it would mean quantum mechanics breaks down at cosmological scales. That's radical. Alternatively, the information might be preserved in subtle ways. Maybe in correlations we haven't yet detected. Maybe in the initial conditions of our Big Bang. Some physicists argue that the seeds of galaxies, those tiny quantum fluctuations that inflation amplified, might actually carry information from a previous cycle. We think of them as random quantum noise, but what if they're not random? What if there's a message encoded in the cosmic microwave background, a message from before? This idea might sound like science fiction, but it's taken seriously by researchers like Roger Penrose. He's looked for specific patterns in the CMB that could represent information transfer from a previous aeon in his conformal cyclic cosmology. Beyond the Hawking points I mentioned earlier, there could be other signatures, spiral patterns, concentric rings, anomalies that don't fit the standard inflationary prediction. The data is noisy and the search is difficult, but it's being done. We're essentially trying to decode a cosmic message written in the temperature fluctuations of radiation that's been traveling for nearly 14 billion years. Now let me tell you about the horizon problem in more detail, because it's central to why we need inflation or something like it. When we look at the cosmic microwave background, we see that the temperature is remarkably uniform. Variations are only about 1 part in 100,000. That means regions of space separated by vast distances somehow equilibrated to the same temperature. But here's the problem. Those regions have never been in causal contact. Light hasn't had time to travel between them since the Big Bang. They're beyond each other's horizons. So how did they know to be the same temperature? It's like finding that two people who have never met or communicated somehow are wearing identical outfits. Coincidence? Highly unlikely. Inflation solves this by proposing that all those now distant regions were once much closer together, in causal contact, before inflation blew them apart. They equilibrated when they were near, then inflation stretched them beyond each other's horizons. Problem solved. But here's the twist. If there was something before inflation, a contracting phase perhaps, then those regions could have been in causal contact even earlier during the contraction. The horizon problem is solved not by inflation alone, but by the pre-Big Bang state. This is one reason why cyclic models and bouncing cosmologies are attractive. They naturally solve the horizon problem without requiring an exponential expansion. There's also the flatness problem. Space appears to be geometrically flat to extraordinary precision. Not positively curved like a sphere, not negatively curved like a saddle, but flat like a sheet of paper, at least on large scales. In standard Big Bang cosmology, flatness is unstable. Any tiny deviation from flatness gets amplified as the universe expands. For the universe to be as flat as we observe today, it must have been incredibly flat in the early moments. Fine-tuned to better than 1 part in 10 to the 60th. That's absurdly precise. Inflation solves this by stretching space so much that any initial curvature gets flattened out, like inflating a balloon until its surface looks flat locally. But again, if there was a pre-Big Bang phase, the flatness could be explained differently. In some cyclic models, the universe naturally approaches flatness over multiple cycles. Each bounce or transition resets certain parameters. Over time, the universe evolves toward flatness and uniformity. It's an attractor state. This means we don't need to assume the universe started out nearly flat. It became flat through a natural evolutionary process spanning countless cycles. This is philosophically appealing because it doesn't require fine-tuning at the beginning. There is no beginning to fine-tune. Let's talk about baryogenesis, the process by which the universe came to have more matter than antimatter. In the early universe, matter and antimatter should have been created in equal amounts. But when matter and antimatter meet, they annihilate. If there had been exact symmetry, everything would have annihilated, leaving only radiation. Yet here we are, made of matter. Galaxies, stars, planets, people, all made of matter with barely any antimatter around. Something broke the symmetry. We call this baryogenesis, the genesis of baryons, the protons and neutrons that make up ordinary matter. Andrei Sakharov identified 3 conditions necessary for baryogenesis. First, there must be processes that violate baryon number conservation. Second, there must be C and CP violation, meaning the laws of physics treat matter and antimatter slightly differently. Third, these processes must occur out of thermal equilibrium so the matter-antimatter asymmetry doesn't get washed out. We know the second condition is satisfied. CP violation has been observed in particle physics, but we're not sure about the first and third. The standard model of particle physics doesn't provide enough CP violation or the right out of equilibrium conditions to explain the observed matter-antimatter asymmetry. This is where pre-Big Bang cosmology could help. Maybe the asymmetry was generated not in the hot Big Bang phase but earlier, during a phase transition from a previous state. Maybe the bounce or the brane collision created conditions that naturally produced more matter than antimatter. Some models suggest that the universe could have had equal amounts of matter and antimatter, but they got separated into different regions or even different branes. Our universe is a matter-dominated region, but somewhere out there, in another bubble or beyond our horizon, there could be antimatter-dominated regions. We can't see them, but they'd be required by symmetry. Another mystery is the cosmological constant. Einstein introduced it as a fudge factor to make the universe static, then called it his biggest blunder when Hubble discovered the universe was expanding. But in 1998, we discovered that not only is the universe expanding, it's accelerating. Something with negative pressure, dark energy, is driving this acceleration. The simplest explanation is a cosmological constant, vacuum energy inherent to spacetime itself. But there's a problem. When you calculate what the vacuum energy should be using quantum field theory, you get a number that's about 10 to the 120th power larger than what we observe. That's not just wrong. That's spectacularly wrong. It's the worst prediction in the history of physics. Why is the cosmological constant so small? This is one of the deepest unsolved problems in theoretical physics. Some argue that anthropic reasoning provides the answer. If the cosmological constant were much larger, galaxies couldn't form, and we wouldn't be here to observe it. In an eternal inflation multiverse with varying cosmological constants, we inevitably find ourselves in a region where it's small enough for structure formation. But this feels like a cop-out to many physicists. We'd like a dynamical explanation, a mechanism that sets the cosmological constant to its observed value. Pre-Big Bang scenarios offer possibilities. Maybe the cosmological constant is not constant at all. Maybe it varies over cosmic cycles or between different phases of the universe's history. In some models, what we call dark energy is actually a dynamical field that evolves. During the big crunch or bounce, it could have very different properties than it does today. The small value we observe might be a transient feature of our current epoch, not a fundamental constant. In future cycles or in other bubbles, it could be completely different. There's also the Hubble tension, a recent crisis in cosmology. When we measure the expansion rate of the universe using the cosmic microwave background and trace it forward, we get one value. When we measure it directly using supernovae and other distance indicators, we get a different value. The discrepancy is about 9%, and it's statistically significant. Either there's some systematic error we haven't identified, or we're missing something fundamental about how the universe expands. Some physicists suggest that the solution might lie in the early universe. Maybe there was an unexpected phase before nucleosynthesis. Maybe there are additional relativistic particles we haven't accounted for. Maybe the physics of the pre-Big Bang era left an imprint that affects the expansion history in ways we don't yet understand. This tension is exciting because it suggests our standard model of cosmology, lambda CDM, might be incomplete. We might need new physics. And new physics in the early universe could provide clues about what came before the Big Bang. Resolving the Hubble tension could open a window into pre-Big Bang cosmology. Let's talk about causal structure more carefully. In general relativity, space-time is more than just a stage on which events occur. It has structure. There are light cones that determine what events can influence what other events. Causality is built into the geometry. When we say the Big Bang was the beginning, we're saying that all causal chains trace back to it. There are no events in our past before the Big Bang. But if spacetime itself is emergent, if it arises from some more fundamental quantum structure, then causality might not be fundamental either. It might emerge along with spacetime. This has radical implications. In some approaches to quantum gravity, like causal dynamical triangulations or causal sets, spatiality is built in from the start. Spacetime is constructed from discrete elements with causal relations. But time, as we usually think of it, emerges from these causal relations. In such frameworks, asking what came before the Big Bang is asking about causal predecessors to the Big Bang event. If the fundamental structure allows for such predecessors, then there can be a pre-Big Bang era even though classical spacetime begins at the Big Bang. The Big Bang is where classical spacetime emerges, but the quantum structure from which it emerges has a richer causal structure. Carlo Rovelli, one of the founders of loop quantum gravity, has written extensively about the nature of time. He argues that time is not a fundamental feature of reality but an emergent one, arising from thermodynamics and our limited perspective. At the fundamental level, the laws of physics might be timeless. The Wheeler-DeWitt equation I mentioned earlier is indeed timeless. It describes the quantum state of the universe without reference to time. Time emerges as a useful concept only when we have a large number of degrees of freedom and take a coarse-grained view. In this picture, the question of what came before the Big Bang becomes a question of how the timeless quantum state gives rise to our perception of time flowing from a Big Bang event. Let me tell you about quantum entanglement in cosmology. Entanglement is that spooky action at a distance Einstein worried about. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Now think about the early universe. During inflation, quantum fluctuations were stretched to cosmic scales. These fluctuations were entangled. Today, we're measuring correlations in the cosmic microwave background that reflect that early entanglement. The universe is, in a sense, a vast quantum experiment that's been running for 14 billion years. But here's where it gets interesting for pre-Big Bang physics. If there was a previous universe or a previous cycle, quantum entanglement from that era might persist through the bounce or transition. Particles or fields from before could be entangled with structures in our universe. This would be incredibly difficult to detect, but it's not impossible in principle. Laura Mersini-Houghton and others have proposed that entanglement between our universe and other universes in the multiverse could leave observable signatures. Anomalies in the CMB, unexpected correlations, cold spots that don't fit the standard model. We've actually observed some of these anomalies. Whether they're evidence for multiverse entanglement or just statistical flukes is hotly debated. There's also the cosmic neutrino background. We've detected the cosmic microwave background, the photons left over from when the universe became transparent. But there should also be a cosmic neutrino background from even earlier, about 1 second after the Big Bang when neutrinos decoupled from the primordial plasma. These neutrinos have never been directly detected because they interact so weakly with matter. But they're out there, about 339 neutrinos per cubic centimeter on average, cooled to a frigid temperature of just under 2 degrees Kelvin. Detecting the cosmic neutrino background would be a triumph, but it's extraordinarily difficult with current technology. However, if we could detect it, these neutrinos would carry information about the universe at 1 second old, much earlier than the CMB, which shows us the universe at 380,000 years. More importantly, precision measurements of the cosmic neutrino background could potentially reveal anomalies left over from pre-Big Bang physics. Maybe a slight excess in certain directions. Maybe unexpected energy distributions. Maybe correlations that point to a previous cosmic epoch. Now let's discuss cosmic strings in more detail. These are hypothetical one-dimensional topological defects in spacetime predicted by some grand unified theories and by string theory. When the universe underwent phase transitions in its earliest moments, symmetries were broken and cosmic strings could have formed, much like cracks forming in ice. These strings would be incredibly thin, far thinner than a proton, but stretch across cosmological distances. They'd have immense tension equivalent to about 10 to the 21st kilograms per meter. That's the mass of Mount Everest compressed into a length smaller than an atom. Cosmic strings, if they exist, would produce distinctive signatures. They'd gravitationally lens background galaxies, creating duplicate images. They'd generate gravitational waves with a characteristic spectrum. They'd leave imprints in the cosmic microwave background as discontinuities in temperature. We've searched for all of these signatures and haven't found them, which places constraints on the abundance and properties of cosmic strings. But here's the connection to pre-Big Bang physics. Different models of what came before make different predictions about whether cosmic strings should form and in what abundance. Detection or non-detection of cosmic strings could help us discriminate between models. Moreover, if cosmic strings exist, they might be survivors from a previous cosmic cycle. In some cyclic models, certain topological defects are stable enough to survive the bounce or transition. They'd be like fossils, relics from a previous universe embedded in ours. Finding such a relic would be direct evidence of a pre-Big Bang cosmos. Alternative theories of gravity are worth considering. Einstein's general relativity has passed every test we've thrown at it, but that doesn't mean it's the final word. Modified Newtonian dynamics, or MOND, was proposed to explain galaxy rotation curves without dark matter. It hasn't been as successful as dark matter models, but it reminds us that our theories are always provisional. Then there are F of our theories, where the Einstein-Hilbert action is modified by including higher-order terms in the curvature. These theories can produce effective inflation without an inflatant field. They can also affect the early universe in ways that might connect to pre-Big Bang physics. In some modified gravity theories, the singularities that plague general relativity are avoided. The Big Bang singularity might not occur, making a smooth transition from a previous state more natural. These theories are constrained by observations, but they're not ruled out. As we gather more data, particularly from gravitational wave astronomy and cosmology, we'll be able to test these alternatives more stringently. Let's consider the thermodynamics of the universe as a whole. The second law of thermodynamics states that entropy, disorder, always increases in a closed system. The universe seems to be a closed system, so its entropy should be increasing. Indeed, if we trace cosmic history forward, entropy grows. Stars burn fuel, black holes form and evaporate, structures dissipate. Eventually, in the far future, the universe reaches maximum entropy, a state of thermodynamic equilibrium called heat death. But here's a puzzle. If we trace backward, entropy decreases. The early universe was in a very low entropy state. The Big Bang appears to have been a state of extremely high temperature but surprisingly low entropy. Why? This is called the past hypothesis. We have to assume that the universe began in a special low entropy state for thermodynamics to work. But it's an unexplained assumption. Why should the universe begin that way? Pre-Big Bang scenarios offer potential explanations. If the universe bounced from a previous collapsing phase, maybe entropy was reset or partially reset at the bounce. Or maybe our universe is part of a larger system where entropy can decrease locally while increasing globally. In eternal inflation, each bubble universe starts with low entropy, but the multiverse as a whole might obey the second law. Roger Penrose has argued that the low entropy of the Big Bang is a serious problem that cosmologists don't take seriously enough. He suggests that his conformal cyclic cosmology addresses it by positing that black holes, which carry enormous entropy, evaporate away completely before the next cycle begins. The end of one aeon is a state of maximum entropy, but through the conformal rescaling, this maps onto the low entropy beginning of the next aeon. It's a clever idea, though not without its critics. Black hole thermodynamics itself provides fascinating insights. Black holes have entropy proportional to their surface area. The larger the black hole, the more entropy it contains. In fact, black holes have the maximum possible entropy for a given volume. This connects to the holographic principle I mentioned before. Information about a volume of space is encoded on its boundary. The universe might work the same way. All the information about what happened in our universe, including what came before the Big Bang if there was a before, might be encoded holographically on the cosmic horizon. This has led some researchers to propose that the Big Bang is a holographic projection. The real degrees of freedom, the fundamental description of reality, live on a lower dimensional boundary, perhaps at the edge of our cosmic horizon or on some mathematical boundary in the space of all possible universes. What we experience as three-dimensional spacetime evolving from a Big Bang is a holographic image of processes occurring on this boundary. It sounds bizarre, but holography has been rigorously established in certain contexts, particularly in the ADS-CFT correspondence in string theory. Let me tell you about the de Sitter space, a solution to Einstein's equations with a positive cosmological constant. It's a spacetime that expands exponentially forever, much like our universe will if dark energy remains constant. De Sitter space has interesting properties. It has a cosmological horizon, beyond which events cannot influence us. It's also maximally symmetric, meaning it looks the same from every point. Some physicists speculate that the fundamental state of the universe is de Sitter space, and what we call the Big Bang is a quantum fluctuation away from this state. In eternal inflation, most of space is in a de Sitter-like state, inflating forever, and our Big Bang was one of many quantum tunneling events that carved out bubbles of slower expansion. If this is right, then de Sitter space is eternal and the Big Bang was not the beginning but a transition within an eternal de Sitter background. This perspective shifts our thinking dramatically. Instead of a universe with a beginning and possibly an end, we have an eternal inflating space with quantum fluctuations constantly creating bubble universes. We live in one such bubble, and the Big Bang is the moment our bubble nucleated. There's also the question of quantum mechanics itself. We use quantum mechanics to describe the early universe, but what if quantum mechanics isn't fundamental? What if it's an approximation that emerges from something deeper? Some physicists are exploring post-quantum theories, frameworks that go beyond standard quantum mechanics. These might be necessary to describe quantum gravity or the very early universe. If quantum mechanics is emergent, then the quantum fluctuations we think seeded the Big Bang might themselves have a deeper explanation. Gerard T. Hooft, a Nobel laureate, has proposed that quantum mechanics might emerge from an underlying deterministic theory. It's a minority view, but it's taken seriously. If he's right, then the randomness we attribute to quantum mechanics is just apparent, arising from our ignorance of deeper variables. This would have profound implications for cosmology. The initial conditions of the Big Bang might not be random but determined by this deeper theory. And that deeper theory might naturally incorporate pre-Big Bang physics. Let's talk about inflation at the quantum level. During inflation, the inflaton field undergoes quantum fluctuations. These fluctuations are stretched by the exponential expansion, becoming classical perturbations in the density of the universe. This is the standard story, but there are subtleties. How exactly does a quantum fluctuation become classical? This is called the quantum to classical transition, and it's not fully understood even in ordinary quantum mechanics, let alone in quantum cosmology. Some researchers argue that decoherence, the process by which quantum superpositions effectively collapse due to interaction with the environment, is responsible. During inflation, different regions of space decohere from each other, and quantum superpositions of the inflaton field become classical mixtures. But if inflation is eternal, there are always regions where quantum effects dominate. The quantum to classical transition is never complete globally, only locally in regions like ours that have stopped inflating. This suggests a picture where the fundamental state of the multiverse is quantum, with classical bubble universes like ours emerging as special, decoherent regions. There's a fascinating connection between quantum mechanics and cosmology through the concept of the quantum state of the universe. In ordinary quantum mechanics, you have a system and an environment. The system evolves according to the Schrödinger equation, and you can make measurements that collapse the wave function. But what about the universe as a whole? There's no external environment. There's no external observer. The universe contains everything, including all observers. So what does it mean to talk about the quantum state of the universe? This question has generated a lot of debate. Some physicists adopt the many worlds interpretation, where all possible outcomes of quantum measurements occur in different branches of the wave function. In this view, the universe's wave function never collapses. It just branches endlessly. The Big Bang wasn't a single event but a branching point where the universe split into countless versions, each with slightly different properties. We inhabit one branch. Others prefer the consistent histories or decoherent histories approach, where you identify sets of histories that decohere from each other and can be assigned classical probabilities. The Big Bang is one history among many possible histories, and quantum mechanics tells us the probability of different histories. In this framework, pre-Big Bang physics would be part of an extended history that includes what came before. Now let me address a practical question. Will we ever know for sure what came before the Big Bang, if anything? The honest answer is maybe not. There might be fundamental limits to what we can observe or infer. Information from before the Big Bang might be irretrievably lost or diluted beyond detection. But that doesn't mean we should stop looking. Science progresses by pushing boundaries. Even if we can't answer the ultimate question, we'll learn enormous amounts in the process. We'll develop better theories of quantum gravity, better understanding of cosmology, better experimental techniques. The journey itself is valuable. Moreover, our concept of what's knowable keeps changing. 50 years ago, the idea that we could detect gravitational waves was absurd to many. Now it's routine. 100 years ago, the idea that we could determine the age of the universe was fantasy. Now we know it to 1% precision. Who knows what we'll achieve in the next century? Maybe we'll develop quantum computers powerful enough to simulate early universe physics. Maybe we'll build detectors sensitive enough to catch the faintest whisper of primordial gravitational waves. Maybe we'll develop a complete theory of quantum gravity that makes clear, testable predictions about pre-Big Bang physics. The point is to stay curious, stay rigorous, and keep exploring. That's what science is about. Not having all the answers, but asking better and better questions. The question of whether the Big Bang was truly the beginning is one of the best questions we've ever asked. And regardless of the answer, the quest to find it will push human knowledge forward in ways we can't yet imagine. Let's address something cosmologists rarely talk about in public because it makes them uncomfortable. The measure problem. In eternal inflation, an infinite number of bubble universes are constantly being created. Infinitely many of them have physics like ours. Infinitely many have different physics. Now here's the problem. How do you calculate probabilities when you're dealing with infinities? If there are infinitely many universes where the electron mass is what we observe, and infinitely many where it's different, what does it mean to say one outcome is more probable than another? Infinity divided by infinity is undefined. You can't do statistics with infinities in the usual way. This isn't just mathematical pedantry. It strikes at the heart of whether eternal inflation makes scientific predictions. Different ways of regulating the infinities, different measures as they're called, give wildly different predictions for what we should observe. Some measures predict that we should see much larger variations in the cosmic microwave background than we do. Others predict we should observe vacuum decay happening nearby, which we don't. The measure problem remains unsolved, and it's one reason some physicists are skeptical of eternal inflation despite its elegance. But here's where it connects to the Big Bang question. If we can't properly define probabilities in an eternal multiverse, can we meaningfully ask whether the Big Bang was the beginning? The question presupposes a framework where we can talk about what's likely or unlikely, what's typical or atypical. Without a proper measure, these concepts become slippery. Some researchers argue we need to abandon eternal inflation or find a natural cutoff that makes the infinities finite. Others argue we need new mathematics, new ways of thinking about probability itself. Then there's the Boltzmann brain problem, named after the 19th century physicist Ludwig Boltzmann. Here's the idea. In an eternally existing universe, or in the far future of our universe dominated by dark energy, quantum fluctuations will occasionally produce localized pockets of low entropy. Most of these will be small, just a few particles. But given infinite time, fluctuations of any finite size will eventually occur, including fluctuations large enough to spontaneously assemble a functioning brain, complete with false memories of a life that never happened. These are Boltzmann brains. Now here's the disturbing part. If the universe is truly eternal, there will be vastly more Boltzmann brains than evolved brains like ours. The number of Boltzmann brains produced by random fluctuations over infinite time dwarfs the number of brains that evolved through the ordinary processes of star formation, planet formation, and biological evolution. So statistically, if you're a conscious observer in an eternal universe, you're more likely to be a Boltzmann brain than a real person. Your memories, your entire experienced history, would be illusory, created by a random quantum fluctuation. This seems absurd, and most physicists think it points to a flaw in our reasoning rather than a genuine prediction. But what's the flaw? If the Big Bang wasn't the beginning and the universe is eternal or quasi-eternal, we need to explain why we're not Boltzmann brains. Some cyclic models address this by ensuring the universe doesn't reach thermal equilibrium where Boltzmann brains could dominate. The universe keeps resetting through bounces or transitions before it gets to that point. Others argue that the measure problem I just mentioned is responsible. With the right measure, Boltzmann brains might not dominate after all. Let's talk about cosmic censorship, another deep principle in general relativity. Roger Penrose conjectured that singularities, where the laws of physics break down, are always hidden inside black hole event horizons. They're never naked, never visible to external observers. This is called the cosmic censorship hypothesis. If true, it means the universe is protected from the chaos of singularities. We can't see them, so they can't affect us in unpredictable ways. But the Big Bang singularity, if it exists, is different. It's not hidden behind a horizon. It's in everyone's past. It's a naked singularity that everything emerged from. This makes some physicists uncomfortable. Maybe cosmic censorship should apply to the Big Bang too. Maybe quantum gravity or pre-Big Bang physics eliminates this naked singularity, replacing it with something less pathological. The Big Bounce does exactly this. Loop quantum gravity's resolution of the singularity does this. These theories respect a kind of cosmic censorship by ensuring there are no naked singularities, not even at the beginning of time. There's also the fascinating question of closed time-like curves, paths through space-time that loop back on themselves, allowing time travel to the past. General relativity permits solutions with closed time-like curves, like the Gödel universe or rotating black holes taken to extremes, but they require exotic matter and violate causality in disturbing ways. Most physicists think closed time-like curves are unphysical, that some principle we don't yet understand forbids them. But what about at the Big Bang or before? Could causality itself be different in that regime? Some approaches to quantum cosmology suggest that near the Planck scale, our usual notions of cause and effect break down. Events aren't strictly ordered in time. There's a quantum foam of possibilities where causal structure is fuzzy. In such a regime, asking what caused the Big Bang might be like asking which came first, the chicken or the egg, in a situation where the answer is genuinely neither because causality doesn't work that way. This connects to John Wheeler's participatory universe idea. Wheeler suggested that observers play a fundamental role in bringing the universe into existence through quantum measurements. It sounds mystical, but there's a kernel of serious physics. In quantum mechanics, the act of observation affects what's observed. Wheeler proposed that on cosmological scales, the universe exists in a superposition of states until observers measure it, collapsing the wave function and determining its properties retroactively. In this view, the Big Bang wasn't fully determined until observers like us came along billions of years later and made measurements that reached back in time to fix what happened. Most physicists find this too radical, but it illustrates how quantum mechanics might fundamentally change our understanding of cosmic origins. The past might not be fixed and determined until it's observed. The Big Bang might be partially created by our observations of it. This doesn't require consciousness or anything mystical, just the quantum mechanical process of decoherence and measurement. But it does suggest that the question of what came before the Big Bang might be ill-posed because the Big Bang itself is entangled with our present measurements. Let's discuss vacuum decay, a scenario for the end of the universe that also has implications for its beginning. The Higgs field, which gives particles mass, sits in what appears to be a stable vacuum state. But calculations suggest it might actually be metastable, sitting in a local minimum but not the absolute lowest energy state. If that's true, the vacuum could decay through quantum tunneling to the true vacuum, releasing enormous energy. A bubble of true vacuum would nucleate and expand at the speed of light, destroying everything in its path. The laws of physics inside the bubble would be different. It would be, in effect, a new universe. This raises a disturbing question. Could our universe be inside such a bubble? Could the Big Bang have been the moment when a previous vacuum decayed and our vacuum nucleated? In this picture, there was a previous universe with different physics, and we're living in the bubble of new vacuum that destroyed it. The Big Bang marks the boundary of the expanding bubble. Beyond our cosmological horizon, the previous vacuum might still exist, and our bubble is still expanding into it at light speed. We'd never see the boundary because it's receding from us faster than light. We're trapped inside this bubble universe, forever ignorant of what lies beyond. Some versions of eternal inflation incorporate vacuum decay as the mechanism that creates bubble universes. The inflating false vacuum occasionally decays to true vacuum, creating bubbles that stop inflating and undergo hot Big Bangs. Each bubble is a universe with potentially different physics determined by how the fields settled into their new vacuum state. Our universe is one such bubble, and the Big Bang is when our local patch transitioned from false to true vacuum. Now let me tell you about the quantum Zeno effect and its cosmological implications. In quantum mechanics, if you measure a system repeatedly, you can prevent it from evolving. It's called the quantum Zeno effect after Zeno's paradoxes. An arrow that's constantly observed at each moment can never move. Similarly, a quantum system that's constantly measured can't transition between states. Some physicists have speculated that observation or decoherence in the early universe might have affected its evolution in unexpected ways. If there were proto-observers or early decoherence events, they could have influenced the quantum to classical transition during inflation or even before. This is highly speculative, but it points to a deep question. Does the universe need observers to become classical? Does observation play a fundamental role in cosmology? Most physicists say no, that decoherence happens naturally without observers. But a minority argues that consciousness, or at least complex information processing, might be necessary for the universe to have a definite classical history. If they're right, then the Big Bang couldn't have happened without the eventual emergence of observers, creating a bizarre loop where the end of cosmic evolution determines its beginning. Let's talk about what specific experiments and observations are planned for the next decade that could shed light on pre-Big Bang physics. The Simons Observatory and CMBS-4 are next-generation cosmic microwave background experiments that will map polarization with unprecedented sensitivity. They're specifically looking for primordial gravitational wave signatures that would tell us about the energy scale of inflation. If inflation happened at energies close to the Planck scale, it strongly suggests quantum gravity was important, and that opens the door to pre-Big Bang physics. The Square Kilometre Array, a massive radio telescope being built in South Africa and Australia, will map the distribution of hydrogen in the early universe during the cosmic dark ages before the first stars formed. This will test inflation's predictions about the initial density perturbations and might reveal anomalies that don't fit standard models. Any deviation from the predictions of simple inflation could point toward more complex scenarios, possibly including pre-Big Bang effects. The European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope will survey billions of galaxies, mapping the large-scale structure of the universe in exquisite detail. They'll measure how matter is distributed, how galaxies cluster, and how this evolved over cosmic time. These measurements constrain dark energy, dark matter, and the initial conditions from inflation or whatever preceded the Big Bang. If the initial conditions show patterns that inflation can't explain, we'll need to look deeper into cosmic history. LISA, the space-based gravitational wave detector, launches in the mid-2030s. It will detect gravitational waves at much lower frequencies than LIGO, opening a new window on the universe. Primordial gravitational waves from the very early universe, possibly from a bounce or phase transition before the Big Bang, would produce a stochastic background that LISA might detect. Even if LISA doesn't see them directly, it will place stringent limits that rule out or constrain various models. Then there are next-generation particle colliders being discussed. The Future Circular Collider at CERN would be 100 kilometers around, 7 times larger than the Large Hadron Collider, and would reach energies high enough to potentially produce particles predicted by string theory or supersymmetry. While these experiments probe high-energy physics, not cosmology directly, they're connected. The same theories that predict new particles also make predictions about the early universe. Finding supersymmetry or extra dimensions would vindicate approaches like string theory and ekpyrotic cosmology. Not finding them would force rethinking. There's also the emerging field of quantum gravity phenomenology, where physicists look for tiny violations of symmetries or modifications to dispersion relations that quantum gravity might produce. Ultra-high energy cosmic rays, gamma-ray bursts, and neutrino astronomy could reveal these subtle effects. If spacetime is discrete at the Planck scale, as loop quantum gravity suggests, high-energy particles might experience slightly different speeds of propagation depending on their energy. Detecting this would be smoking gun evidence for quantum gravity and would support bounce scenarios where quantum gravity resolves the Big Bang singularity. Laboratory experiments are also relevant. Quantum simulation of early universe physics using cold atoms or superconducting circuits might allow us to test aspects of inflationary dynamics or bounce scenarios in controlled settings. We can't recreate the Big Bang in a lab, but we can create analogous systems governed by similar mathematics. These analog experiments are already teaching us about Hawking radiation from black holes using sound waves in flowing fluids. Similar techniques might probe aspects of cosmological phase transitions or bounces. Let's address the philosophical implications more directly. If the Big Bang wasn't the beginning, it changes how we think about existence itself. Western philosophy and theology have long been preoccupied with the idea of creation, of a first cause. Aristotle argued for an unmoved mover. Thomas Aquinas argued for God as the first cause. The Big Bang seemed to provide a moment of creation that science could identify, even if it didn't explain the creator. But if time extends before the Big Bang, if the universe is eternal or cyclic, there's no moment of creation. There's just existence, ongoing and perhaps infinite. This is closer to Eastern philosophical traditions like Buddhism and Hinduism, which have always embraced cyclic time and eternal existence. The universe goes through endless cycles of creation and destruction, with no ultimate beginning or end. Modern cosmology might be converging on a similar picture, not through philosophy but through mathematics and observation. It's a remarkable example of how scientific discoveries can resonate with ancient wisdom while being arrived at through completely different methods. But what does this mean for meaning itself? If the universe is eternal, if our Big Bang is just one event in an infinite sequence, does anything matter? Some people find this depressing, a cosmic nihilism where nothing has ultimate significance. Others find it liberating. We're not constrained by some cosmic purpose or divine plan. We create our own meaning. Our lives matter because we decide they matter, not because the universe has inherent meaning. I lean toward the latter view. The fact that the universe might be eternal and purposeless doesn't diminish human experience. Love, beauty, discovery, creativity, these things are real and valuable regardless of whether the universe had a beginning. In fact, perhaps they're more valuable precisely because they're temporary and local. We're brief patterns of complexity in an possibly infinite cosmos, and that makes each moment precious. There's also the question of whether understanding our origins changes how we behave. Does it matter for ethics or politics whether the Big Bang was the beginning? Probably not directly, but it matters for how we see ourselves as a species. We're cosmological creatures, products of 14 billion years of cosmic evolution, or perhaps much longer if pre-Big Bang physics is real. We're made of atoms forged in stars that died before our sun was born. We're capable of understanding our own origins through science. That's profound, and it should inspire both humility and pride. Let me tell you about one more cutting-edge idea before we wrap up. The holographic cosmology, or ADS CFT duality applied to cosmology. This is highly mathematical, but here's the gist. String theorists have proven that certain gravitational theories in curved spacetime are mathematically equivalent to quantum field theories without gravity in one fewer dimension. This is the ADS CFT correspondence, one of the most important discoveries in theoretical physics of the past 30 years. It tells us that gravity, in some sense, is an emergent holographic phenomenon. Researchers are trying to extend this idea to cosmology. If our universe is holographic, the Big Bang might correspond to some event in a lower-dimensional quantum field theory. The four-dimensional spacetime we inhabit, including its history from the Big Bang to now, might be encoded in a three-dimensional boundary. Understanding what happens on that boundary could tell us what came before the Big Bang in our four-dimensional description. It's like watching a movie and then discovering the film reel exists in a different dimension, and by studying the reel, you can learn about scenes that were never shown. This is speculative, and the mathematics is fiendishly difficult, but progress is being made. If cosmological holography works, it would revolutionize our understanding of the Big Bang and provide a completely new perspective on the question of cosmic origins. The Big Bang would be a holographic projection, and what came before would be encoded in the boundary degrees of freedom that project it. We're living through a golden age of cosmology. For the first time in human history, we're gathering data that can actually test ideas about the origin of the universe. We're not just philosophizing or creating untestable myths. We're making measurements, doing calculations, and confronting theories with reality. The question of whether the Big Bang was truly the beginning is shifting from philosophy to science. In the next 20 years, we'll have data from missions and experiments I've mentioned. We'll have more sensitive detectors, bigger telescopes, more powerful computers to simulate early universe physics. We'll either confirm the standard Big Bang inflation picture, or we'll discover anomalies that demand new physics. Either way, we'll learn. That's the scientific process. We're building knowledge brick by brick, observation by observation. And let's be clear about something. Even if we never definitively answer the question of what came before the Big Bang, the quest itself drives progress. The theories we develop to address this question advance our understanding of quantum gravity, high-energy physics, and cosmology. The instruments we build to test these theories make other discoveries we never anticipated. The mathematical techniques we invent have applications beyond cosmology. Science is not just about reaching final answers. It's about the process of inquiry itself. So here we stand, a curious species on a small planet, looking back through time to the very edge of our cosmic horizon. We see the Big Bang, that moment 13.8 billion years ago when our observable universe began its expansion. For decades, we thought that was the beginning, the alpha point of space, time, and matter. But now, armed with sophisticated theories and increasingly powerful instruments, we're peering beyond. We're asking what came before. We're taking seriously the possibility that the Big Bang was a transition, a bounce, a phase change, a birth but not the first birth. This is what humans do. We push boundaries. We ask impossible questions and then figure out how to answer them. We're not satisfied with, "That's just how it is," or "We can never know." We probe. We test. We imagine alternatives. Sometimes we're wrong. Often we're wrong. But occasionally we're right, and when we are, we see further than anyone before us. We add another chapter to the human story of understanding reality. The Big Bang may not be the beginning after all. What an incredible realization. It would mean the universe is even grander, even more mysterious than we thought. It would mean our story extends further back, perhaps infinitely far back, into a past we're only beginning to glimpse. It would mean that every time we think we've found the ultimate origin, we discover there's another layer beneath, another question to ask. And maybe that's how it should be. Maybe reality is like an infinite onion, layers all the way down, each one revealing new structure, new physics, new mysteries. We'll never reach the bottom because there is no bottom. There's just deeper and deeper understanding, forever. That might frustrate those who want final answers, but it should excite anyone who loves discovery. It means the adventure never ends. There will always be new frontiers, new questions, new horizons to explore. As I stand here, thinking about all this, I feel incredibly fortunate. Fortunate to live in an age when these questions can be asked scientifically. Fortunate to witness the birth of gravitational wave astronomy, the mapping of the cosmic microwave background in exquisite detail, the development of theories that actually make testable predictions about the origin of everything. Our ancestors looked at the stars and wondered. We look at the stars and measure. We calculate. We predict. And sometimes, gloriously, we understand. So whether the Big Bang was the beginning or just a chapter in a much longer story, whether time extends infinitely into the past or emerged at some quantum moment we can't quite define, whether our universe is alone or one bubble in an infinite multiverse, one thing remains constant. We keep asking. We keep searching. We keep reaching out with our minds and our instruments to touch the deepest mysteries of existence. That's what makes us human. Not our intelligence alone, but our curiosity. Our refusal to accept ignorance when knowledge is possible. Our drive to understand where we came from, what we are, and where we're going. The cosmos has given us the gift of consciousness and curiosity. The least we can do is use them. The Big Bang may not be the beginning after all, but our quest to understand it is just beginning. And in that quest, in that relentless drive to know, we find our meaning. We are the universe awakening to itself, asking questions about its own origin, marveling at its own complexity. We are cosmology's way of comprehending cosmology. And that might be the most remarkable thing in all of existence. Keep looking up, keep questioning, keep wondering, because out there, in the data yet to be gathered, in the theories yet to be developed, in the observations yet to be made, lies the answer. Or at least the next question. And that's enough. That's more than enough. That's everything. The universe is calling. Let's answer.